Okay, so let's get started. Before that, let's go through a quick review or recap of what we did in the last class, right? So essentially, we started looking at what is called the inner product, right? So how do you generalize the notion of similarity or the dot product of two vectors, right? And we listed out all the properties of a simple dot product, and then we generalize that to any function, right? It takes two vectors and maps to a number. So what are the properties that this particular function should satisfy so that it can mimic inner product? Then it turned out to be, it should be bilinear. That's one property. If you take inner product with itself, it should be non-negative, and it should be symmetric, right? So these are the properties. Of course, if you are working with complex numbers, then it's not symmetric that way. It's Hermitian symmetric, or U Hermitian V is same as V Hermitian U. So it's not. So it's not like V transpose U is same as U transpose V, but V Hermitian U is not same as U Hermitian V, right? So there is a conjugation difference. So you have to take care of that. Okay, so then we looked at what is called the induced norm, right? For example, if you look at A transpose A, that gives me the Euclidean length squared, right? So similarly, if you take any inner product of a vector with itself and take the square root, that should induce what is called a norm, right? So this is the norm induced by the inner product. So that's what we looked at. And then we also saw that this norm, or the notion of length, satisfies certain properties, right? First of all, it's non-negative because it's length. The second thing is, if you look at the length of the scaled vector, it should be the length of the vector scaled by that much, right? It's a modulus of alpha times the vector, and the triangular inequality. And this length notion will induce distance, the distance based on length. Similarly, if there is a norm induced by an inner product, then the distance can be written as norm of U minus V, right? This is the distance. This is a distance notion induced by this norm. So when you look at a space, a vector space with an inner product and an induced norm, that space is called what is known as an inner product space. Okay, for example, Rn is an inner product space, and there are so many others. We will look at a few more today. Okay, so now then we also saw an example of how to, for example, if you have not so intuitive space and we have to measure similarity, how do you do that? Well, towards that, we saw that, we looked at this example. You look at all functions which are continuous and square integrable. I can define my own inner product here, and that inner product will induce a norm, and therefore it becomes an inner product space. And I can also define the distance, and naturally I can define what is known as similarity of two functions. All that I have to do is I have to take F4 norm of F, G over norm of G, and take the inner product, right? So that gives me this notion. So this also leads to, if you do the same thing for random variables, it leads to correlation coefficients, right? That's what we did in the last class. And then we also looked at a very important inequality called what? Cauchy-Schwarz inequality, right? So essentially, inner product absolute value is less than or equal to the product of norms. That's what it says, right? And we also looked at how to prove it. Okay, so today we will continue with the inner product. Let's look at another inner product